Next, we want to look at bow waves, sonic booms, and how musical sounds are produced. All right, so we were going to look at what are called bow waves and how they relate to something called the sonic boom. Now, in the example of the Doppler effect, we talked about how if a bug is moving as it's producing waves, that those waves will bunch up. But what would happen if the bug is moving at the same speed that the waves are moving? If the bug is moving at the same speed, the waves would not be able to get out in front of the bug. And so they would be completely compressed on the side that the bug was moving, and they would spread out on the other side. And that would create what's called a wave barrier, because if the bug is moving at the same speed as the wave, the bug can never get ahead of the wave. And if you were over here somewhere, you would not be able to hear the waves at all until the bug got close enough to you that essentially the bug got past you. Now we can look at what happens if the bug is actually able to move faster than the waves themselves can move. In that case, the bug basically gets ahead of the wave. So you can see, this circle here is the most recent wave produced by the bug, when the bug would have been at its center. But the bug is moving faster than the wave, so by the time the wave gets to here, the bug has already moved past it. And so this creates a sort of overlapping of the waves that gives a characteristic V shape. And that's kind of like the shape of the bow of a boat. So imagine that you are in a speedboat traveling through the water, and I've sort of drawn a crude sketch of one here. As the boat cuts through the water, it's going to send out these sort of V-shaped waves. And so if you were here, as the boat moves past, it would drag the waves with it. So when the boat is kind of here, that wave would now be where it would be swept past, and you would actually feel the wave come past you there. And so the boat actually has to go quite a bit past you for you to feel the wave, because the boat's dragging the wave behind it, in essence. In any case, that's a bow wave. And this, with the boat, that's an example of a bow wave in water. But you can also have, for example, a bow wave in sound. Now, if, for example, you have a plane flying through the air, it's going to create sort of a three-dimensional bow wave behind it. If it's traveling faster than the speed of sound, the sound waves are going to bunch up, and it's going to create this sort of three-dimensional bow wave. And if you were down here, you would not hear the plane at all, because the sound wave hasn't reached you yet. So the plane is flying overhead, you're right here, but the plane would drag this bow wave with it, or actually this is in this three-dimensional bow wave we call a sonic boom. And so as it dragged this guy towards you, eventually you would make contact with this wave and you would hear the sonic boom of the wave, but you wouldn't hear the plane until it had already flown over you, because it's moving faster than the sound. If the plane was moving slower than the sound it made would be moving faster, and it would be able to reach you before the plane reached you. But if the plane is moving faster than the sound, it will reach you before the sound does. Now that sonic boom, actually the term that we would say we call that the shock of the wave, or the shock wave. And here is this is called a Schlieren photograph. Schlieren photography is a way of taking a picture of sound waves. And you can see a bullet, which is traveling faster than sound, has got this bow wave, or this shock wave, that is surrounding it. And you can see that it's emanating from the tip, and there's also one emanating from the rear end as well. And those two together, they make up the entire shock wave. Now, here we have a depiction of the shock wave. So the plane is traveling faster than the speed of sound, and we have the shock wave coming from the tip and from the tail. And actually, as we've seen, this creates sort of a three-dimensional cone around the plane. And the shock wave consists of the part from the front of the plane all the way to the part emanating from the back of the plane. And what happens if you were on the ground right here, As the shock wave passes you, the first part, the part corresponding to the nose of the plane, that would be a very high pressure bunching up of the sound waves. And so you would feel the shock of those sound waves hitting you, and then the pressure gets very low towards the tail end of the plane. And so you can see the shape of the pressure versus time. It's first a very high positive pressure, and then the pressure gets very low and actually is negative here. You can see this is called an N wave because of its shape, and that's the characteristic pressure profile of a shock wave. And so, again, just to be clear, here we have a plane that's generating a shock wave, or what we like to call a sonic boom, because that just sounds cooler. The sonic boom, the plane is flying. So when the plane's over here, none of these guys have heard the sound or heard the plane because the plane's moving faster than the sound. As it goes here, we see the snapshot. This is right when person B hears the shock wave because it's sweeping past him. Now this person at point C has already heard it. It's been already dragged past him, and so he's felt the front end high pressure and the low pressure back end of the shock wave. It's all passed through him. This guy's just now experiencing it, and this guy has yet to experience it, but he or she will when this guy moves further enough to the left to drag this shock wave with it so that it intersects him. And that is how sonic booms work. Wow, we've already covered a lot of things in this chapter, and we are still not done. Isn't that crazy? Well, the good news is this is the last topic for this chapter, but it's a really cool and interesting topic. It's the topic of how musical sounds are produced. What is it that makes something a musical sound and something else noisy? So, for example, if I hit a particular pipe with a hammer, I get a nice tone, like a musical instrument tone. But if I hit something like just a random rock with a hammer, I hear a clonk, it's not very musical at all. So what is it about the sound when we hear it that makes it seem musical or not musical? And so the difference between a musical tone and a noisy tone is the way that the waveform looks. And so you could imagine the pressure waves emanating from the thing making the sound. Here would be an example of a noisy kind of a sound. And you can see there's a lot of randomness here. The waves, there's just a lot of mess here. That's what makes a sort of a noisy sound. Now, the lower case in part B, we see something that might be more characteristic of a musical tone. So you can see it's much smoother, and while there's some structure here, it's a much smoother structure, and there's repetition. And so the two things, see here it's all random. There's nothing repeated anywhere. It's just a bunch of random pressure variations. But here, the pressure variations are in a pattern, they're nice and smooth, and they're repeated. And that's the kind of thing that gives rise to a musical tone rather than a noisy tone. But how does that come about in the first place? Now, there are lots of different ways that you can produce musical tones, and they can be quite different from one another. The way that a piano produces its musical tone is quite different from how a trumpet or a clarinet or a drum would produce their musical tones. And explaining all the differences between all the different kinds of instruments, that's a lot, and it's way more than we want to cover in this course. But what we do want to get across to you is sort of the basic idea. So here's a picture of the different harmonics of a guitar string. And this could be a piano string or any other kind of string. And all the things that we're going to talk about here would be applicable to reed instruments like clarinets or wind instruments like trumpets or, all the different kinds of instruments. They have their own ways of generating the sound, but these general wave principles apply to all of them. Now, I told you in a previous video that everything has its own natural characteristic that it wants to vibrate at. And that's true. And if you strike something, it's going to tend to want to vibrate at its natural frequency. What I didn't tell you yet is that things can also vibrate naturally at what we call the higher harmonics. and that would be double the fundamental frequency, or triple, or quadruple, some multiple of the fundamental frequency. Things can vibrate at those different frequencies that are multiples of the fundamental. And so here we have a depiction of a guitar string, and these are some of the different ways that the guitar string can vibrate. And so, of course, the guitar string can vibrate at its fundamental frequency, and that would be the lowest frequency that the guitar string could vibrate at. But the guitar string could also vibrate at what we call its second harmonic. And so here you see the half wavelength of the fundamental tone. Here you see the full wavelength of the second harmonic. Here you see 1.5 wavelengths of the third harmonic. That would be a vibration. The string is vibrating at 3 times the fundamental frequency. And of course, down below we see the fourth harmonic. Incidentally, whatever harmonic you have one more node than that. So the first harmonic has 2 nodes. The second harmonic has 3 nodes. Remember, the nodes are the points in the standing wave where the vibration doesn't go up or down any. It just basically stays at rest. And I don't remember if I mentioned it or not, but these are actually standing waves in the string of the guitar. So we have these different standing waves that exist at the different harmonic frequencies. Now, here's the thing that you have to wrap your head around. When I pluck a guitar string, it doesn't just vibrate at one of these. It doesn't just pick one of them. It's simultaneously vibrating at all of them. And so it's going to be mostly vibrating at the harmonic. That would be the loudest vibration. But there's also going to be a bit of second harmonic and a bit of third harmonic. And the string's going to be vibrating some at the fourth harmonic. All of these happen all at the same time. And when you add those sounds together, that's what makes it sound like a guitar string rather than a piano string. Now, each instrument has its own recipe. So 2 instruments could be playing the same note, but the quality of the sound would be very different because each instrument is producing different amounts of harmonics. So when I said it's like a recipe, this is what I mean. A piano string, when you strike it, it might have this much harmonic plus a certain amount of second harmonic plus a certain amount of third harmonic and fourth harmonic and so on. The guitar string, when you strike it, or rather when you pluck it, it might have different amounts. So it might have a certain amount of first harmonic that's different from the piano string. It might have more second harmonic than the piano string and less third harmonic, or vice versa. The thing is, I don't know what the exact combinations are for different instruments, but each instrument has its own combination of this much fundamental plus this much second harmonic plus this much third harmonic and so on. And that's what gives each instrument its unique sound, its unique quality of sound. And incidentally, the musical term for that is timbre. The timbre of the instrument is basically describing how these harmonics are combining. So here's how we can see that working in practice. We have our fundamental frequency, which is just like a pure sine wave. And then you have the second harmonic and the third harmonic. And if you add all of these 3 together, that would be, a string has been struck or plucked or whatever, and it's producing all these together. What you end up with is a wave that is smooth and it's repeating its pattern, but it's not like a pure sound wave. So it doesn't sound like a pure sound wave. It sounds like a piano or like a guitar or whatever it is. Let me give you an example of that. Here is a pure sound wave. This is a 440 hertz A sound wave, the musical note A. So hopefully you heard that pretty good. It's kind of a boring sound, right? It's just, it's not any kind of structure to it at all. That's a pure sound wave. Now let me play that very same note on a piano. Could you hear the difference, how much richer the piano sounds? It's because the piano has all of those higher harmonics that are being generated at the same time. and that makes it a much richer and fuller sound. And visually, we can see sort of the difference between, say, a piano playing a C, that is the musical note C, and a clarinet playing the musical note C. You can see there's a lot of similarities. The fundamental, you can kind of see the time it takes for the pattern to repeat is the same in both cases. You can see that you've got this maximum here, then it reoccurs here, it reoccurs there. For both instruments, you see the shape of the wave is more or less the same. But inside that sort of envelope of the wave, you can see that the wiggles are different. The wiggles inside the wave are different because what's happening is different amounts of harmonics are being added together to create that different timbre or that different characteristic of sound. And that's the basic idea of how musical sounds are produced instead of, say, noisy sounds. And I hope you found all this interesting and illuminating, but now we have enough understanding of how waves work that we can also apply some of these ideas to light waves, which is the topic of our next chapter, and it's what we'll be covering next.